Hello, everyone. Thanks so much for coming. This is F Sharp for C Sharp programmers. My name's Scott Wlaschin. I have a website, fsharpforfunandprofit.com, which I think kind of gives away my bias. So I'm a big fan of F Sharp, and I will try not to be too biased. I'll try and present why I think this is an interesting language for you to learn. But if I go overboard, like, you don't have to trust me. You can look for yourself. So the goal of this talk really is just to demystify F Sharp a bit. A lot of people think that functional programming is very scary, and there's monads and weird mathematical things. I'm just going to try and demystify it a little bit, just so that you can kind of maybe get interested in investigating it. Obviously, you can't become an expert in an hour. So, and I'm not going to go through, this is not going to be one of those feature things where I show you all the features of the language, because I think that's the kind of stuff you can learn by yourself. I'm going to talk about more like the philosophy of the language and how functional programming is different from object-oriented programming, and how F Sharp has a different philosophy than C Sharp in terms of how you do things. So, is it worth the effort to learn another new language? It's like, there's all these new languages. There's Rust, and there's Go, and there's Kotlin, and it's like, is it really worth it to learn a new language? So this is a quote that I like. A language that doesn't affect the way you think about programming is not worth knowing. So, for example, if you know C Sharp, learning Java is not going to change the way you think about programming. So it's not worth learning Java. I mean, it might be worth learning Java to get a job, but it's not worth learning it to try and expand your mind, right? On the other hand, I think F Sharp is a language that will change the way you think about programming, and so I do think it's worth putting an effort in to learn it. Here was a conversation I saw on Reddit, I think. Someone said, well, yeah, F Sharp is a little bit better, but is it really worth the effort, Which I sympathize with. I mean, it's like there's so many new things. You really don't want to spend a lot of time learning something, if you're not going to really get anything out of it. But somebody responded with this, learning F Sharp was a big boost to my career as a C Sharp developer. So this person doesn't use it professionally. There aren't that many F Sharp jobs, but we're talking about personal development here. We're talking about learning new paradigms, learning new ways of programming. And he said this knowledge actually made me a better programmer in general. So that's a good reason to learn F Sharp. Another way before you put a lot of effort into something is to find somebody who has done it before. So find someone you trust who has learned C Sharp and has also learned F Sharp, and ask them, is it worth learning? And if they say yes, you don't have to trust me, but don't trust people who just look at it and say it's horrible. Don't bother, because you need to have experience in both sides, and only then can you make a sensible decision. So find someone like that and ask them what they think. All right. So some misconceptions about F Sharp I'll just clear up quickly. It's developed by Microsoft Research, not Microsoft proper, but it became a proper Microsoft product in 2010, shipped with Visual Studio. And now it's on a parity with C Sharp and VB and so on. Parity in quotes. It's open source. I think it's one of the first Microsoft products to go open source. It's on GitHub. You can change the compiler and put a pull request in and go for it. It's cross-platform. It works on Linux. It works on Windows. It works on the Mac. It works with .NET Core. It works with Mono. Obviously, it works really well in Visual Studio, but it also works really well with other editors of Visual Studio Code. Has a fantastic F Sharp plugin called Ironide, which I highly recommend. And there's also things for Emacs and Vim and so on. Really important, active and friendly community. When you're learning a language, you don't want people to tell you off asking stupid questions when you're beginning, right? You want people who are supportive. So if you go to fsharp.org, which is the F Sharp Software Foundation, there's instructions on how to download. There's also instructions on how to get to the F Sharp Slack channel, there's a beginners channel in there. You can ask questions. And on F Sharp on Twitter, the hashtag, that's a great place to ask questions or to find out what's going on with F Sharp. Right, so what am I going to talk about? So the first thing I'm going to talk about is the differences between C Sharp and F Sharp. When you're learning a new language, you always want to kind of compare it with what you already know, and that's true for anything. I actually think that's a bad idea, to be honest. I think when you're learning something new, especially if it's a completely different paradigm, you should actually have like a beginner's mind and forget everything you know, because it's going to interfere with your learning. So ideally, when you're learning a language like F sharp, you should forget everything you know about C sharp. That's kind of impossible, but that would be the recommended approach, because otherwise you're going to get frustrated and say, well, why doesn't it do this and why doesn't it do that? But since you're here, and since you are C sharp people, I'm going to talk about the differences anyway. So the first thing is the syntax is very different, and this is probably what you see first, and this is what puts a lot of people off, and I'll talk about that. Type inference is something which is very different between F sharp and C sharp. The defaults are different. So in F sharp, everything defaults to immutability, for example, and mutability is something special. And there's a different philosophy about what's important when you program. And then I'll talk about things which are sort of special to F sharp that C sharp doesn't have. The fact that F sharp is a functional first language, the fact that F sharp has an algebraic type system, and the fact that F sharp is an interactive language. You can play with it like Python or Ruby. It feels like a scripting language. These differences between C sharp, by the way, I've ranked them from least important to most important. People really focus on the syntax. That is the least important thing about a language. The fact that it's got a different philosophy, I think, is more important. But it's not obvious. Just by looking at the code, it's not obvious that it has a different philosophy. But I'll talk about that. So let's start with the syntax, because this is a thing that people really complain about. So what I'm going to do is I'll start off with a C sharp example, and I'll mutate it, so I'll transform it into F sharp code. So here's an immutable class in C sharp. It's a person class, it's got a name property and a birthday property. It's a pretty dumb class, really. All right, so the first difference in the syntax is indentation rather than curly braces, and you've probably seen this. Here's all the curly braces, and the question is, do we really need them? Do they add value, right? If you look at C sharp code, I think 1/3 of C sharp code is curly braces. Is it really that important? The indentation already gives you everything you need to know. So this is the code with curly braces, and this is the code without curly braces, with indentation, okay? There's the code with curly braces, there's the code with indentation. Now, some people will say, well, is it really that harder to read without the curly braces? Some people say yes. It's like, oh no, this is like impossible to read. I can't possibly understand this code. Really, that's a silly thing to say. Okay, so if you, there's a couple of things to notice. First of all, you might have noticed I put equal signs. That's used to start the blocks. Whoops. And the other thing is that we can shift without the curly braces, we actually get a lot of vertical space back. So we get a lot of vertical space compaction, which is very nice. So if you're worried about white space, here is a helpful Venn diagram. There are people who complain about white space, and there are people who've used a language with white space, and the intersection is a very small intersection. There are some people who do complain and who've used it, but normally people who complain actually haven't done it. So people complain about Python, but they've never actually used Python. Okay. Here's Eric Raymond, who is, can't get much more hacker credentials than that. He said Python. So he's talking about Python, which is very similar to F sharp in terms of the white space. The Python's use of white space stopped feeling unnatural after about 20 minutes. I just indented code like I would with C, and it worked. All right? And that's pretty much, you just indent it the way you would normally indent it, and pretty much things work. That is not the hardest part about learning F sharp, believe me. So, give it a go. Don't let this white space thing bother you. How many people here know Python? Okay, well then you've got no problem. No problem with F sharp. All right. Okay, here's some other syntax differences. I'll just go through quickly. A lot of these things are also going to be available in C at some point. If they're not available now, I'm sort of losing track of which features are actually making it into the C releases. But first one, backing fields from constructor parameters. If you look at the constructor, there's a name and a birthday, and then there's a backing fields which are name and birthday, and there's just a lot of names, but it's like duplicate stuff everywhere, right? That's annoying. Let's get rid of it. So in F sharp, the parameters that you pass the constructor automatically become backing fields, so you don't need to define them. And then you can just, in your property, you can just return it. That saves a bit of code right there. Okay, that's very nice. The primary constructor and the class definition get merged. So in C sharp, the constructors are separate kind of methods, as it were, separate from the class definition. In F sharp, you take this constructor and you put it at the top. Because how often do you have more than one constructor? I mean, sometimes you do. And in F# you can have secondary constructors too. That's not a problem. But almost always, why not just like make it part of the class definition like that? That saves a bit more. It also saves some more vertical space. That's another 3 or 4 lines we've saved right there. Less noise. Okay, so this is an immutable class. We've got all these gets everywhere. Get. Let's get rid of the gets. Okay, the gets are gone. That's good. Another thing we don't need is semicolons. Nobody likes semicolons, right? Everybody hates semicolons. Let's get rid of them. Now, occasionally you do have 2 things on the same line, and you can use a semicolon if you need to, but you don't need to normally. Right, okay. No return. So in C# you have a return keyword to tell you this is the return of the method or whatever. In F# you don't need it. And code looks like this. And the reason is that F# is an expression-oriented language. Everything is an expression, not a statement. So an expression is something that returns something. It's not just, it doesn't just do something, it always returns something. It's like if in C#, it's like the difference between an action and a func, right? Everything is a func in F#. There's no actions. It always returns something. And so if it always returns something, you're always going to need a return statement, so you just make the last line of the block be the return. So in this case, the name is the last line, that's what gets returned. All right, so you've got implicit returns. That's very nice. All right, public members. Okay, so this is a mutable class. People can't change it. Why make everything private? So in, it's noise. Like in C#, you spend a lot of time typing public. Like, let's not get rid of it. Let's get rid of the public. We don't need public. Now, in F#, this is a good example where the defaults are different. In F#, you can make things private if you want to. You can have the same accessibility modifiers. You can say private and internal and all that stuff. The defaults are different. The default is public. In C#, the default is private. All right, type inference. Okay, so in the constructor, we say that the name is a string and the birthday is a date. And in the properties, we say the name is a string and the birthday is a date. It's like, why are we duplicating this? Why can't the compiler figure this out? Why do we have to keep typing the date time over and over, right? In F#, the compiler does figure it out for us, right? We specify it once, and then thereafter it's figured it out. Now at this point, our properties are kind of getting hard to know their properties. They're getting sparse. So in F# you have to say that something's actually a member. So that's a little bit of a clunky thing. You have to say this is a member this dot. So this is the self. It's the same as this in C#. It's the self-reference. Okay. And so that indicates a class member, and use the same syntax for methods as properties. So this is a method, age, and you calculate the age by doing something. And again, I don't have to return. I just say that the difference divided by 365, that's the age. So methods and properties look very similar in F#. And notice that with age, I didn't have to say it returned an int. Right? The compiler figured it out. All right, type annotations. So in C#, types come before the variable name. So date, time, birthday, string, name. In F# it's the other way around. The types come afterwards, so it's birthday, colon, date, time, name, colon, string. If you've ever used TypeScript, it has the same thing. A lot of languages do this. Most modern languages now kind of adopt this kind of a standard way of doing types. So the C kind of languages have their own way of doing it, but other languages do it this way. Different keywords. Okay, now if you care about, this is the kind of syntax difference that really, if you care about this, I'm sorry, I can't help you. Different keywords. So in F#, in C# we use class and we use var. In F# we use type and we use let. All right, and those different keywords, but really, that's all you have to remember. It's not that hard. All right, now modern C# does have a lot of these features. When I wrote this, I think I wrote this based on, I haven't done C# for a while, so I've kind of lost track of what's current. But this is an example where the constructor is merged with the class definition. It's got auto properties. It's got expression-bodied members and so on. So it does kind of look like C#, except for the fact you've got public and you've got the duplicated types and everything. And the expression-bodied members only work for single lines, and it's, but it's the same idea. I mean, conciseness is good. Conciseness is really nice if you can do it. All right, now that was the object-oriented syntax I showed you. The functional programming syntax is even simpler, because all this member stuff, it's kind of ugly. So in functional programming, the key thing is you separate the data structures from the behavior. So the functions that act on the data are separate from the data things themselves. So in F#, if I wanted to define a person, I would define it like this. So this is what we call a record type in F#, and it kind of looks a little bit like JSON, I suppose. There's a name and there's a birthday, and that's the type. This is an immutable data structure with two properties. There is no behavior. It's just like, you can think of it as a DTO as well. It's like a dumb object with no behavior. If I want some functions that work in it, I define separately, I define an age function. And the age function looks like that. So again, it's let. There is one parameter, which is person, and there's a space between the parameters. And that becomes important later on when you do things like partial application. So in functional languages, you tend to use spaces between the function parameters. Notice that I didn't have to, what else have I got? Yeah. I don't have any type annotations, but the fact that I'm passing a person and the person has a birthday, it figures out that the person is a person type, and it figures out there's an int return. So if I look at what's inferred, the type inference will say, this is a person to int function. I don't have to specify that, which is very nice. So there you go, that's type inference is great. And so it kind of looks like, if you're used to Python, this looks very much like Python. You're not specifying any types anyway, you're just kind of writing code and, but unlike Python, this is strictly typed, so you'll get a compile error if you make a mistake. So, as I said, syntax is not the most important thing. It's never the most important thing about a programming language. But, okay, I'm going to make an exception. Originally, we had like 21 lines of code. Now we've got 5 lines of code if we take those two properties. We'll find if you compare C# and F# code bases, where it's actually pretty much the same code being rewritten, we'll find that F# code in general is about 3 times less, 1/3 of much F# code as C# code, because of the vertical compression, because of the lack of braces, the lack of null checking, the fact that you don't have constructors and stuff. There's just a lot less code. And that's I think that's kind of important, even though syntax is not that important. I think the fact that you can see 3 times more on your screen, it's like getting a super large monitor. So that's nice. And you only have to write 1/3 as much code. So that's nice too. So that's not, like I say, syntax is not that important, but I think conciseness is important. And I think C# can sometimes be a little verbose, But that's not I wouldn't say that's not the only reason to use a language. So just let you know, there's other more important reasons. Type inference. Okay, so that's the syntax stuff. Type inference. Here's a function, do something, and it's got some parameters, an f and an x. And let's say we're going to add 1 to x, and we're going to pass it into this f. So f is obviously some sort of function. And then the output of that function is a y, and then we're going to take y, and we're going to add it to hello. So I haven't specified anything in the parameters, right? So can the compiler figure out what's going on? And the answer is yes, it does. And the way it does it like this. First of all, it says that x has to be an int, because anything you add to an int has to be an int. F#'s really strict. There's no kind of coercion between types. So you can't add a float to an int, and you can't add an int 64 to an int 32. They're all different. So it knows that x has to be an int. And then it also knows, because you're passing into f must be a function. Now, what about y? Y has to be a string for the same reason. If you're going to add something to another string, y has to be a string. So now, if we look at f, we know that the input to f is an int, and the output of f is a string, so it's an int to string function. And so finally, this is the inferred type, okay? The first parameter, f, is a function, which takes an int and returns a string. The second parameter is an integer, and the return type, the very last line, is a string, because that's hello plus something. So the type inferences works like this. It can do quite a lot of stuff. Occasionally you need to annotate types, but in many, many cases you can just write code like this and it just works. Okay, so that's all very good, but is it really, how useful is that really? I mean, it's kind of saves some typing. Let me show you a more complex example, okay? This is the group by extension method from link, and I challenge you to scan this and figure out what exactly it does. There's a lot of noise here, Sometimes you can't even find the name of the method because it's buried under all the stuff. I mean, this is nice, it's nice to know, but there's a lot of noise, and if you're writing your own functions, you're going to have to figure out what all these types are yourself and annotate them properly. In F#, the code looks like this. Okay, almost always the compiler will figure out all this stuff for you, which is kind of cool. So the benefit of type inference is obviously less typing, but more importantly, less noise. You can really focus on the logic of the code and not worry about the kind of types get in the way. Again, if anyone who's used a dynamic language like Python or Ruby, you don't really need to see all the types every single time. In Visual Studio and in VS Code, you can actually hover over the thing and it will tell you what the types are. And there's a code lens thing. I mean, there's lots of things that will tell you what the types are without having to type them explicitly. All right, different defaults. So the different defaults in F#. It's immutable by default. Mutability is a special case. Everything is non-null by default. And if you want nullability, that's a special case. Everything, the F# record types and stuff are structural. You get structural equality by default. And reference equality is a special case. Or for classes and stuff, you get reference equality. So structural equality means that if all the properties are the same, then the two things are the same. I'm sure you've overridden equals and get hash code to do that a million times, right? And then everything must be initialized. That's a big difference. So let's start with immutability. So there's a value in F#, x equals 1. Now in F#, the assignment operator is not equals. The assignment operator is the backwards arrow, like that. It's a different thing altogether. So you can't, assignment and equality are not going to get mixed up. So we're going to assign 2 to x, and if we try and do it, the compiler is going to complain and says it's not mutable. Okay. Now, if I do want a mutable value, I have to use the mutable keyword. And then when I assign it, it's happy. So this is saying that mutability is something you have to ask for. It's not something that happens by default. And because you have to ask for it, and because it's so explicit, you tend to use it less. You know, it's like you tend to, because we're lazy, right? We tend to use whatever's easiest. If things in C#, we can create read-only classes in C#, but it's kind of a pain, so we tend to not bother so much. Everything tends to be mutable. You know, we tend not to do it this way. In F#, it's the exact opposite. Everything's immutable by default, and so if you're lazy, you just follow the flow and make everything immutable. And very occasionally, you need things to be mutable. What about nullability? So here's our person type. If I do this, I'm going to say this is x is a person, and I'm going to assign it to be null. I get a compile time error. Person doesn't have null as a value. Okay, this is very different from C#, where you can assign null to most classes. If I do want to assign null to a class, I have to do it like this. Okay, I have to say allow null literal attributes on top, and I have to use a special class and so on. It's like painful, right? I mean, it does work if I do this, but because it's much more painful, you're really never going to do it. The only reason you might want to do it is to be backwardly compatible with something, you know. But you're never going to use this in real code. So you're never going to write, you can pretty much rely that all your classes in F# are never going to be null. And that's nice because you eliminate null checking. If you ever write defensive code in your constructor, you know, if the parameter is null, throw an exception or whatever, you never see that kind of code in F# because you can guarantee that nothing's null. Okay, structural equality. So here's our person type again. Now let's say that we have this crazy rule that if someone has the same name and they have the same birthday, they're the same person. All right, not a very good rule, but I've seen that actually done in practice. So here's Alice version 1, Alice version 2. Both these things have the same name, they have the same birthday. The question is, are they equal? Is Alice version 1 the same as Alice version 2? And the answer is yes. In F#, that is true. You do not have to override get hash code, and you do not have to override equals to get this. This is the default behavior. And that's a great relief to me because I hate writing equals, and I always get it wrong, and I worry that there might be some special case when the two things are null and I haven't checked it properly. It's like, I can never remember how to do it right. I probably have bugs in my code. And the same thing with get hash code. Hate writing it. Right, so you never have to write. That's one big relief there. Okay, everything has to be initialized. Okay, here's our person again. Okay, so in C#, you can say, here's a variable, here's a backing field or something, and it's just going to be a person. Now in C#, that can be set to null. The default value for a class is null. In F#, that's an error. Okay, you can't, there is no default value for anything. Null is certainly not a default value because it's not a nullable thing. So you always have to initialize it to be something. So you never have an uninitialized variable in F#. And if you partially initialize it, let's say you set the name but you forget to set the birthday, that's also an error. Every single property is required when you initialize it. So if you add a new property, all your code will break until you fixed it, which is probably good, I think. I don't know. You know, you never have this thing where you've added a new property and somebody forgets to initialize it properly because you've got a constructor which is backward compatible, and you know that's never going to happen in F#, which is kind of nice. So you can trust. A lot of it's to do with trust. You can trust that things have been properly initialized. So you tend to not write defensive code in F#. You don't have to check for null. You don't have to check, is it initialized? Is it a valid object? All that stuff tends to disappear. So that's another reason why the code is shorter, because there's just a lot less defensive programming. All right, so here's what I think is the most important thing, which is a different philosophy. So C# obviously is derived from C-like languages. Obviously, it doesn't have pointers and stuff like that, but it's got the imperative model. You have for loops, you have mutability, and so on and so forth. Now, F# is a cousin of ML, which is a language designed in the 1970s, pretty much around the same time as C. And that ML stands for meta language, and it was originally designed for proving things. Okay, so it wasn't really designed to be a kind of useful enterprise programming language. And that means there's a different philosophy. And so let's look at an example of a philosophical difference. And let's talk about predictable code. So what I mean by predictable code is, can you understand the code in front of you just by looking at it? Okay, you're not allowed to look at the documentation. You're not allowed to look at the rest of the code base. You're not allowed to look at the implementation or anything. Just by looking at the code in front of you, can you tell what it does? Right? And if you can, that's great, because that's more or less makes understanding the code much easier. So here's some code. X equals 1. Do something with X. And Y equals hello plus X. So the question is, what is Y? Well, in C#, this wouldn't work. But if I told you the answer is hello world, would that give you a clue? No, the answer is you can't tell. This is a trick question, actually. This is actually JavaScript. Okay, it was not C# at all. This do something function in JavaScript changes what X is from an int to a string. And it does it silently, so that when I come back later and I use it, it's now a string. And Y is now hello world. Okay, this is horrible. This is horrible. This is like code you can't, this is an example of why you can't trust JavaScript. In C# that could never happen because you've got static typing. You can't change the type of something, magically behind the scenes. So this is an example of C# being more predictable than JavaScript. If you look at the C# code, you know for a fact that it can't compile just by looking at the code. You don't have to, look at the implementation of do something to figure out that it's not going to compile. So this is good. This is the kind of thing we want. So let's take this, extend this, and look at some other things. So let's say we're trying to make a predictable language. Rule number 1, you're not allowed to change the type of a variable once you define it. That's a very good rule. Okay, let's look at another example. 2 customers in C#, they have the same ID and the same name. Are the customers equal? Well, you can't tell, because it depends on whether the customer class has overridden get equals or not. Get hash code and equals and all this stuff. You can't tell, because behavior in the object-oriented world, you're not supposed to know about the behavior of an object. Objects are meant to be opaque, right? So you can't tell. I think to make the code predictable language, if they have the same values, they should be equal. Okay, now I'm not saying that has to be true, but this is on this particular set of guidelines, making things predictable. It makes life much more predictable. Okay, here is a customer and here is an order, and they both happen to have the same properties and the same values in those properties. So the next question, is the customer equal to the order? All right, can you tell? Well, you might say, well, it depends on how they've overridden equality and so on. It's like, no, that's the wrong answer. This is probably a bug, right? If you've accidentally compared the two things by mistake, why would you ever compare a customer to an order? That's like it's a bug in your code. You've typed the wrong thing. So ideally, your compiler would say, you're not allowed to, this is a compile error, you're not allowed to compare two different things, right? So from predictability point of view, that should be a compile time error. Okay, how about another one? Let's say you create a customer, and then you say the customer has an address, and the address has a country, and what is the value of that? What is the address.country? Well, what's going to happen? Are you going to get a null reference? Are you going to get, who knows? Maybe the customer has initialized the address to something valid. I don't know, I can't tell, all right? Because the constructor has no parameters. So, and we can probably assume that it's probably been left as null, but we can't tell. If the address is not required, if it's an optional thing, then we should make it a special optional type. Don't just set it to null. So here's another one. Whoops. Always initialize objects to a valid state. We want the compiler to enforce this. Okay, that way we guarantee when we look at an object, we know that it's in a valid state. We never have to test whether it's null. We never have to test whether the address has been set, and so on and so on. And if it's not a valid state, it's a compile time error. Okay, here's another one. We got a set of, we have a customer, we add it to a set, and then we do something with the customer. We don't know what happens to that customer. And next question, is that customer still in the set of customers? True or false? And the answer is, we don't know. Because the process customer, when you could have mutated the customer and you might have changed its hash code. And when you look it up again, it's in a different place so that you can't find it again. Okay, that's the problem with mutable stuff. Now, if you had something where it was an immutable customer and you do something, if the process customer changes it, it's going to have to return a new thing. It's going to be right there in your face that it's returned a new changed version of the customer. And if it hasn't changed the customer, then it's not going to return anything. But you know, if it doesn't return anything, it can't possibly have changed the customer. So immutability is great there. And in this case, the original customer has never changed, so the hash code can't have changed. It's always going to be existing in that set. So you can rely that things are going to work. Immutability is very useful in terms of knowing and trusting that your code is not going to break, So here's all these things we talked about. Can't change the type. Oh, I've got one more. So yeah, objects and collections should be immutable. It makes life really easy. Now, these guidelines is about immutability, about predictability. Now, you might say, well, I need mutability stuff for performance. I might need it in an array because I've got stuff. It's like, yes, the guidelines for good performance are different from the guidelines for predictability, and they collide. Sometimes performance is more important than predictability. Sometimes predictability is more important than performance, and you just have to choose. But if you're going for predictable, immutability is the best thing to go for. One more. So let's say we have some sort of customer database, and we're going to get a customer using its ID. Okay? So what is the output? What is the ID? We return this customer type value. What's the ID of that customer? Well, what happens if the customer is missing? Okay, let's say you can't find it in the database. What is that customer? Is the customer null, or is it you're going to throw an exception, or what? I don't know. Can't tell. If the customer is null, if you're going to use null as the convention, then the rest of the code is going to break. If you're going to throw an exception as the convention, I'm going to have to look at the documentation or something to figure it out, right? What you really want to do is do something like this. Return something which is the customer or the error. And now you can handle two different cases. If there's a customer there, you can get it, and if it's an error there, you can get it. But by making it a special type called customer or error, you've made it explicit that this thing might work, might not work, and if it doesn't work, here's the error case. You don't have to look at the documentation to figure out is it null or not. Okay, so these are all the rules. No missing data, no nulls. Okay, so try to document things using the type system. So F# aims to be a predictable language like this. You're not allowed to change the type of variable. Objects with the same values are equal by default. Objects of different types can't be compared. Objects have to be initialized to something. Objects are generally immutable. Missing data errors are made explicit by using special types. If you use a null, that's considered a code smell in F#. If you throw exceptions for control flow, obviously sometimes you throw exceptions because you just can't handle something, that's fine. But if you're trying to throw an exception, a file not found exception, that's for control flow. You shouldn't throw exceptions for that. So in F# you tend not to do that. So F#'s not perfect, obviously. There's backdoors and you can't always trust it. But you can see that the kind of conventions lean in a certain direction, the philosophy behind what you think is good code and bad code. Like in C# null is not necessarily a code smell. In F# it is a code smell. So that's kind of a philosophical difference between the two languages. All right, so that's the end of the differences. Now let's look at some of the things which are kind of unique to F#. And the first thing about F# is a functional first language. Now what do I mean by that? F# is a hybrid language. You can do OO programming and you can do functional programming. But it leans towards functional programming. We tend to do the functional stuff first. That's our kind of go-to. If we can use object-oriented programming in the, if there's a particular need for it in a certain situation, but generally we prefer to use functional programming if we can. So let me just quickly, for people who are not familiar with functional programming, I'm just going to quickly give you some things about functional programming. So functional programming, functions are the most important things in functional programming. They're the building blocks for everything. The way that you combine functions is composition, so like Lego. So in an object-oriented language, you make classes that contain other classes, and you build bigger classes in them. In a functional programming language, you create functions out of smaller functions, and you compose functions to make bigger things. That's how it works. And parameterization is really important in functional programming. So if you want to share code, you don't want to repeat yourself and you want to have shared code, you tend to use parameters rather than base classes, rather than using inheritance or something. Parameterization is the way of doing it. So, in functional programming, functions are things, and I think of it like a little bit of railway track with a tunnel on top. There's an input, there's an output, like the input's an apple and the output is a banana. So you see apple, arrow, banana. So here's in F# you write the code like this. To define a normal thing, you say let x equals 1, and to define a function, you say let add equals this, and that gives you a bit of railway track. Notice that in F# we use the same keyword, let, to define normal values, simple values, and also to define functions. That's not a coincidence, because in F# functions are treated like things. Okay, so the difference between a thing like an integer and a thing like a function is not that big a difference. So it's a standalone thing, a function, and because it's a thing, it can be used as inputs and outputs to other functions. So here's our railway track, here's an input, and the output could be a function, for example, because it's a thing. Or you could have a function as the input to a function. Or you could have a function with an input and output, and there's an extra parameter, which is another function, which is controls how the function works. Think strategy pattern, for example. Strategy pattern is exactly the same thing. So this is the basic model for how you do stuff in functional programming. And that's it, really. That's pretty much all you need to know. You can see that it gets quite complicated. Functions that return functions that return functions can get quite complicated. But the concepts are basically straightforward. So let's look at composition quickly. So composition, you have two functions, and you want to glue them together. In F#, that's the double angle bracket. And you glue them together, and now you get a new function. Now what's interesting is that you can't tell that this new function was built from smaller functions. Right? The fact that how it was built is now hidden from you. So for example, where did the banana go? Right? In the low-level code, you care about bananas, but when you get to the high-level code, bananas aren't important. So you've now abstracted away that the bananas were ever involved. Right, so that's how you kind of do abstraction. In F#, let's say we have some functions. If I want to compose them, I use the double angle bracket again. So here's a new function. The add function glued together with the double function, and I can just call this as a new function. I can just call it with, say, 5, add 1 at 6, double it as 12, so that's the answer. Right. So I just basically glued two little functions together to make a bigger function. And I can do that with like 3 functions, same kind of thing. All right, so this is, you can see that it's really easy in F# to do this. It's like, you can see the language is designed to make this easy. Let's look at it in C#, see how easy it is in C#. So in C#, here are our functions, and first of all, we don't get the type inference, so we have to define what the types of the functions are. And if we want to compose functions together, we have to have a special extension method called compose. And that extension method is not built into C#, so we have to write our own. It's not that hard to write, but you could write code like this, but nobody would understand it unless you were a functional programmer already. If you already knew functional programming, this would be fine. But I wouldn't write, if I was in a C# code base, I wouldn't write this kind of code because most of my colleagues wouldn't be able to understand what I'm talking about. So it's just not natural in C#. C# is not a functional first language. Another thing you do in F# a lot is, another kind of composition is piping. So let's say you have a function, you add 1 to 5, and then you want to double it, and then you want to square that. In typical languages, you have these nested parentheses, and they get deeper and deeper and deeper, and you kind of lose track. These nested function calls can get quite confusing, right? You lose track. Where does it start? I have to kind of go down. An alternative way of thinking about it is as a pipeline. So you start off with 5, and you feed that into the add function. The output is 6. You take the 6, you feed it into the double function, you take that, and you feed it into the square function. So this pipeline-oriented model, and I think it's just a lot easier to understand. Same concept, same end result, but a just different kind of conceptual way of thinking about it. And in F#, you have the same pipeline. So if you used to Unix, the vertical pipe, right, piping things on the command line, same kind of thing, except that the pipe character in F# is a vertical bar with an angle bracket. So in F# you tend to see the bottom kind of code rather than the top kind of code. The top kind of code is kind of ugly. The bottom kind of code is very much more common. And you can do the same thing in C#. Define some functions, define a pipe helper function. But again, I would never write code like this in C#. So you can do it. So this is the difference. It's not that you can't. It's not that you can do it. It's something in F# that you can't do in C# and vice versa. I mean, obviously in theory they're equivalent, but in practice, it's you tend to do things in a certain way because the language makes it easy. The language C# does not make it easy to do this kind of functional programming stuff, and in F# makes it easy. Okay, here's another one. Parameterize all the things. So here is a function that prints the numbers 1 to 10. All right, this is F# code. And the first thing we do, if we're an experienced programmer, is say, why have you hard-coded 10? What happens if you want to print 1 to 11 or 2 to 17 something? Don't hard-code the numbers. Pass the numbers in as a parameter, right? Like that. So it's second nature to us to parameterize this kind of stuff. Don't hard-code something when you can pass it in as a parameter, right? Second nature. Now, if you're a functional programmer, you say, well, you've hard-coded the behavior as well. It's like, well, what happens if I don't want to print it? What happens if I want to, do something else with it? Right? Don't hard-code the behavior. Parameterize it. So a functional programmer would parameterize the action that you take as well. You just make another parameter, and this is what you do with each thing in the list. And now what we've made is we've actually made a much more generic design because we've decoupled the action, the list, the action and the looping. They're all now completely separate. So we've actually got a more decoupled design. In fact, this is no longer just printing a list. It could be doing anything with a list. It's iterating over a list and doing something. It's easy in F# because you can just stick the parameter right there. It's really easy to do. You just type it, and you don't have to worry about what type it is. What is the type of action? I don't know. The compiler will figure it out for me. So it's very easy to do, which is why people do it. Again, it's just a natural behavior in F# to do this kind of thing. Let's look at a more complex example. Let's look at, say that we have a product and a sum. And obviously there's some duplicate code here. And don't repeat yourself, right? So what can we do to not repeat ourselves? So what we're going to do is we're going to notice that some of the code is common. The looping through the list is common code. But the initial value is different, and the action that we take each time through the loop is different, right? So we have some stuff which isn't common and some stuff which is different. So what we naturally do is we parameterize the stuff that's different, and keep the common code the same. So here's how it would look in F#. The function that does this is called fold. We have some parameters. We have the action parameter and the initial value parameter, and then the list of things. So we're going to say the total so far is the initial. We're going to initialize it to the initial value. I'm going to use a mutable here just to make it look like the C#. There are other ways of doing it in F#, but just to make it look the same. And for each item in the list, we're going to run the action on the total so far, and the new item in the list, and that's going to give us another total. And at the end, after we've gone through every item, we have the final total, and that becomes the return value. So there you can see that we've got the common code, we've got the initial value, and we've got the parameterized action. So this is how you'd write that code in F#. And once you've done that, you can go back and you can write the product and the sum in this way, using this list fold function. And there's the initial value, and there's the action. What's cool about doing it this way is that we've got a lot more focus now on what's the difference. In the original C# code, a lot of the code was the common code, and it was hard to see what was special about each case. By making it parameterized, it's very clear what the difference in the initial value is, and it's also very clear what the difference in the action through each loop is. And the actual loop logic is, something we don't care about. If you're doing link, this is the same as link aggregate. This .fold is the same as link aggregate. And in F#, there's lots and lots of collection functions like this. And one of the challenges when you're learning F# is to memorize what all these functions are, because there's like 100 of them, and they're all slightly different. Definitely worth spending some time figuring out what they all do. All right, so there's a lot of topics to talk about functional design patterns. I have a whole talk about functional design patterns. If you go to my website, FP Patterns, or just Google for functional design patterns, and I think you'll come across the talk. All right, another thing about F# is this algebraic type system. So F# types are different from classes, okay? A type is not a class. A type is more like a set. And this is something very important to kind of get into your head. So what is a type? So if we have these functions, there's a set of inputs and there's a set of outputs, right? So a type is just the name that you give to a set of things that can be used as input. So you have all these integers, we're going to give it a name. We're going to call it integer. That's the name of the set. All these strings, we're going to give it a name. We'll call it string. So the string type is just a list of every possible string in the world, right? If you have a person type, it's just a set of all the possible people in the world. If you have a flute type, it's a set of all possible flute in the world, right? Since it's just a set, it can be anything. So you can have a set of functions. So this is the set of all functions that work on flute. So this is, each of these functions has a flute input and a flute output. So it's a flute-to-flute function. This is the set of all flute-to-flute functions. So we call that the flute-to-flute type. So anything can be a type. Now, because the types are just data, because it's just a set, there's no behavior, it's really easy to glue them together. And you can use composition just like you can for functions. And that's why it's called an algebraic type system, because just like an algebra where you can add things and multiply things, in the F# type system you can add types and multiply types. So again, we're going to use the Lego analogy. Now, there's two ways of gluing types together in F#. You can AND them and you can OR them. Okay, and I'll explain what that means in a second. So that's basically two different things. So the AND, what does it mean to AND? So let's say you have fruit salad, and a fruit salad is one each of an apple and a banana and a cherry. Okay. Now, that is the common, this kind of ANDing together. A name is a first name and a last name. An address is a street and a city and a postcode, whatever. This is what you're used to in all languages, have a data structure like this. Okay. And in F# you'd write it like this. Okay. So a fruit salad is an apple property and a banana property and a cherry property. All right, that's something that you're very familiar with. The other way is something that you probably won't be familiar with, unless you've had experience with functional languages. Often you will have a choice of things. A snack is an apple or a banana or a cherry. It's a choice. One of these things, not all of them, but one of them only. And this is the kind of type that's not available in C#. And in F# it's called a discriminated union type or a sum type. And in this case you use the vertical bar. So it's an apple or it's a banana or it's a cherry. Okay. These are really, really useful types. One of the things I miss in C# that's in F# is like, even forget about the functional program side, this is fantastic. And we'll see why in a minute. So let's look at an example of how you might do this. So let's say you have a business requirement that you're going to accept card payments for an e-commerce, and you can, or you can accept cash, you can accept a check, or you can accept a credit card. Right? So if there's cash, there's no other information. If there's a check, you need a check number. If there's a credit card, you need a credit card type and a card number, and so on. So how would you implement these requirements? Well, if you're a C# programmer, you'd probably say, well, okay, I'm going to start with some sort of base class or some interface or something, and then I'm going to create a cash class that inherits from it. I'll create a check class with some extra data that inherits from it. I'll create a card class with some extra data that inherits from it, and so on. So that's probably that's sort of the object-oriented way of using inheritance. Now, that's fine, except that you've now got 4 different files, probably, because you wouldn't put them all in the same file. It's kind of a little bit ugly. Let's look at how F# is very different. So in F#, you build the system by composing smaller types. So we start off with some simple primitive types. We're going to say the check number is an int, and a card number is a string. So those are just primitives. And then we're going to say that a card type is a Visa or a MasterCard. So that's an OR type, a choice type. And then we're going to say a credit card is a card type and a card number, and that multiplication, that's the pair, that's the F# symbol for tuple. That's a pair of those things. And now our payment method is a choice. It's either cash or it's a check or it's a card. And if it's a check, there's some extra information. And if there's a card, there's some extra information. And then we'll say, okay, the payment amount is another primitive type, and then the currency is a choice between euros and dollars. And then finally, our top-level payment is going to be an amount plus a currency plus a method, so that's an AND. So what we've done here is we've built a complex type in 20 lines of code without writing any real code. So this is a great way of doing kind of design. Okay, you can get this on one piece of paper. It's really nice. So you can see it's a very different way of thinking about how you construct your domain model. So this is one of the principles in F#. You use types as kind of executable documentation. So if I showed you this is F# code. Can you guess what domain this is? Right, just by looking at the code. Even if you weren't an F# expert, can you guess what this is? I think you can. You can say, well, it's something to do with playing cards, right? And you can see that a suit is a choice between a club and a diamond and a heart and whatever. A card is a pair, a suit and a rank, and a hand is a list of cards, and a deck is a list of cards, and a player is a name and a hand, and so on and so forth. Those are the nouns. You can also document verbs. So to deal is a function, and you start off with a deck. That's your input. The output is a new deck, because the deck's immutable, so now you're going to have a deck with missing a card, and you're also going to have a card on the table. So that's the output. Similarly, when you pick up a card off the table, the input is your hand plus the card on the table. That's the input. And the output, you have a new hand, and the card on the table's now disappeared, because everything's immutable. So you've got a different hand. It's not, you haven't mutated your hand. You have a different hand with this extra card in it. And it fits on one screen. So it's documentation, and it's also code. This is compilable code, which is very nice. Here's another example of executable documentation. If I show you this and I say, what payment methods are accepted? It's like really obvious, right? Now, with the OO thing, I'd have to look in 4 different files. I'd have to find all the things that inherit. It's not really obvious just by looking at the code what payment methods are accepted. I'd have to look at some documentation, probably. So I think this is really nice if you're trying to do like domain-driven design or something. So another big topic, I don't really have enough time. I have a whole talk on domain-driven design and designing with types, and I am doing that talk this afternoon. I also have a book coming out soon. It's in early access right now. It should be out in a couple of months. So that's basically this topic. Right, interactivity, the last thing, and I've got a few minutes left. Before I forget, I just want to say that don't forget, if you're interested in F# or any other functional language, there is a lab where anyone can show up and you can ask questions of the functional track people. So the functional track, I think, is in this room all day and all tomorrow. And if you're interested in functional programming, just stay in this room. And if you've got questions, like I say, come to the functional lab and you can ask questions of people and we can do code demos and stuff. And there was something else I was going to say. I can't remember what it was now. Right, interactivity. So I've got a few minutes left, and let me just show you some interactivity. By the way, F# fun is a keyword in F#. I just want to point that out. I'm not trying to imply anything, just purely by coincidence. One thing about F#, I think it is a fun language. I mean, I don't think anyone says, "Oh, I love programming in C#. It's fantastic," or Java. I think the thing about functional language is because it's concise, it feels like a scripting language. So you feel like you can just like type stuff and it kind of works, which is very nice. So I am going to switch to Visual Studio, if you can see that okay. Yep. So let me show you some code. So here's some real F# code. So this is, in F#, you have this is F# script, but in F# you can actually like highlight code and you can run it interactively. I'm going to say execute in interactive. And what happens is it pops up down here at the bottom. I don't know if you can see that. So basically it's run this piece of code, just this one snippet of code. And I can interactively play with it. It's like, oh, that's interesting. I wonder what happens there. And I can say, add 1 to 5. And it's like, it doesn't have to compile. I can just like run it, Alt-Enter, and that's 6. So that's very nice. So here's a classic thing. Think of a number. This is a game. Think of a number, add 1 to it, square it, subtract 1, divide by the number you first thought of, subtract the number you first thought of, and the answer is 2. Okay, so this is kind of a children's thing. Now in F#, this is how you'd write it, you see. Okay, add 1, square it, subtract 1, divide by the number you first thought of, subtract by the number you first thought of. Okay, there's our functions. And then we just pipe them. So you start with the number you first thought of, you pipe it into add 1, you pipe it into square it, you pipe that into, So this code looks very much like the requirements. This piping model is great for this kind of thing. It kind of looks like your code. So, and what I can do is then like run it and see. I'm going to highlight everything, and there it is. Notice that I didn't specify what kind of function it was, and it's figured out that you pass an integer and it returns an integer. That's nice. Okay, think of a number. If I pass in 10, hey, the answer is 2. If I pass in 11, the answer is 2. And, because it's so easy, and let's see, log it. And then I'm going to return. So here I'm going to use a semicolon to, what's the problem? Oh, I need to pass the X in there. There we go. Right, and then so this is how easy you can it didn't tell me what the original number was. So I'm going to do this. I'm just going to stick it in the pipeline. I've got a new helper function that logs the input. There's that. So I can play with it interactively. I'm going to go down here, highlight it all again, and try it again. And now this time it says A. It's because I've got a bug in my code, because I didn't say this is an integer. There we go. So the nice thing about interact, I didn't have to write a unit test. I could play with it and find a bug. All right. So by playing with it, I already found a bug, and it's like it took me seconds to fix it. So this feels like doing Python or JavaScript, or maybe not JavaScript, but it certainly feels like Python to me. Very nice, very easy to work with. I'll do one more quickly, and I've got about a minute left. So this is a Roman digit converter. So I'm going to define a type Roman digit. So I'm going to use a choice. And I'm going to say, okay, a Roman number is a list of digits. And to convert a digit to an int, I'm going to say, well, if it's an I, that's a 1. If it's a V, it's a 5, and so on. And then I'm not going to really go through the code, but I'm just showing you that this is what F# code looks like. I'm going to map it, and then I'm going to sum it. So here's my digits, and then the answer is 16. And if I change the digits to be XX, then the answer is now 26. And I put another 1 in here, and it's now 27. So you can see, it's really easy to play around with. This is one of the, like I say, it's a fun language to work with. Right, so that's the demo. Like I say, it feels like a scripting language, a lot of fun to work with. And that is it. Thanks very much. The slides and the video will be up on my website in a couple of weeks under C#. If you want F-sharp consulting, we have a consulting company, F-sharp Works. Most importantly, if you want to know more about F-sharp, fsharp.org is the place you should go. So thanks very much. And don't forget to fill in the thing when you go out. Thanks so much.